Hello everybody and welcome back to what seems to be the last episode of us writing our UEFI bootloader, of course. So we just need the final step, which is handing off the execution to our kernel, and that's what we are going to do today. The keen-eyed amongst you will have noticed that I have a new color scheme on my NeoVim setup. So I needed an even darker color scheme than the last one I had, just to make things pop a little bit more and create a bit more contrast. So this color scheme here is a very dark color scheme that I called Tasogare, which is Japanese for twilight. Right, so I guess let's get started. I'm gonna remove the thing here. I'm gonna do set the log level to info because we should not need any of that rubbish. And I'll just build this and we'll see what we go from there. Let's actually give it a run. Sure, this one is fine. Let's see what other things we need to remove. So we do have quite a few of these mmap info things that don't really belong in info, I think. So first thing I'm gonna do is change that. Right, so let's go right ahead and do that. So mmap, and I'll look for just pretty much everywhere we have info. For example, this one here, this should be a debug log. Where else do we have info? Oh, I guess this one should belong in debug too. And the rest is pretty much okay. I also want to get rid of that big square that we have, big red square that we have on our screen now. So I think it's under fill rect. And if I go all the way back here, yeah, so we've hard coded the width and height to 250. I'll change that to 10, just so that we can have a subtle visual marker that we did our visual or our video initialization. Right, so let's rebuild this and see that we have a clean output. Right, so I can see the red square, 10 by 10 red square in the corner there, so that's fine. We don't really have any weird log entries that we don't need, so we can move on to what we really wanted to do. Right, so we want to hand off execution to our kernel, and I think we are going to, or we are not going to be too far off what we did in this here, so let me bring that up here. Yeah, so this one here, switch long mode, and this should be in the assembly somewhere. So I think this is it. Right. Actually, before we do this, I just want to make sure of something. So let's do warn. There should be no, or don't use boot services after this line. And here I'll do to do, and I'll do exit boot services. There we go. So just so that we know where we're going with this. Right, so here we are not going to need this anymore. I'm just going to comment it out because we cannot use boot services after this line since we're going to exit the boot services here. Right, but for now, what I want to do is just check that I can write assembly code into my zig file and that I can see it in the output binary. I think the last time we've written any assembly in zig should be here in this io.zig. So let me just remind myself what this looks like. So we have the ASM keyword with an optional volatile keyword, then parentheses, then we have all the code here. Then we should have a first column, which is the outputs. And then we have the second column with all the inputs. And then a third one with, I believe these are the Clobbered registers. Yeah, seems like it. So let's just do a quick test here. So ASM volatile, and of course put that there. And here we can just do move arrayx. Let's do something here. 0, 1, 2, 3, 4, 5, 6. And I also wanted to move rbx some value that I'll call test val. Right. So the first column is for the in outputs. We don't have any. The second one is for the inputs, and here I should tell it that test val goes into some register, whichever one it chooses, and that the value that we are putting in it comes from a variable value. Right, so let me just do this. This should be a U64, and this should be equal to 0x. That beef, of course. Right, so let me build this and see where we go from there. Actually, let me just remove these two here. Okay, so what is going on here? Unknown use of instruction mnemonic without a size suffix. What the actual flip? Keyword? Do we actually need to do this? I mean, should know what Rx's size is. Okay. Expect token in argument list. Okay. Oh. Okay. Okay. So, I think we should be using AT&T style assembly. Who the flip uses AT&T style assembly? That's the actual question. So I think $for immediate values and % for registers. Wow. That's some weird shit. And here we wanted to do, and of course the source comes first and the destination comes second. So this one would be test val, and this one would be rbx, I think. So give it a try. Okay, so that was it. Fine. That's not what I wanted to do. I wanted to so go over here, do this, and do LVM opstamp -d build boot.uefi. And if I look for 0x13456, there we go. So what do we have here? So deadbeef is the value of test val. We move 13456 to RAX, and then we move RAX to RB. Hold on, 1 second. Just gonna have to do this. I'm gonna use something normal. Right. I'm gonna use something that we can actually read. Right, okay. So we move the beef into EAX, then we move whatever this is. So this is the value, the immediate value that we've put into RAX, and then we move RX into RBX. There's a problem in this. We wanted to have deadbeef into RBX, but here it gets overwritten with this. Oh, right. Okay. Okay. So I think if I do say that RX is clobbered, it should produce bird code. There we go. And now if we go for that again. Okay, so now it puts it into ECX, moves this into RAX, and then moves RCX into EBX. Okay, so that looks pretty good. So now we know that we have our assembly in the file. It's not getting modified, it's not getting any weird transformation done to it. So we should be good to go. Right, so for now, I'm just going to remove this. I'm going to remove these two. And let's think about what we want to do here. So here we are doing shit with CR0. So that means that so CR0 is basically the register that controls the paging. So I think here the first step we do, since we are ANDing it with 7FFF, and this basically here is all ones except the most significant bit 31, which is set to 0, and bit 31, if I remember correctly, in CR0 is the paging bit. So here we are disabling the paging in CR0. Here we do something with CR4. Yeah. So here we are enabling, I think, floating points and SSE, if I remember correctly. I don't have the Intel documentation open for now, so this is just from what I can remember. Right, CR3, this one here is, so set the page map. So CR3 has the address of our page map root. This one here, we are doing a read MSR, so this should be ether, and we should be setting long mode enable, or just do enable long mode. yeah, so we are reading its value, enabling it. I think this bit here, bit 2, is longer mode enable, and writing it back. And then here we are doing something again with CR0, and I think we are enabling the paging. And here I think we are, so we are getting something, putting it into EBX CDX and pushing that, and then popping it back to RX. So here we are pushing our entry point to the stack. Here we are changing our change code segment to 64 bits, and here we are popping entry point from stack, and here is handoff execution to kernel, and this one here is just a catch all in case the kernel returns, which should never happen. Right, so what should we do in our case? Should we disable paging? I don't think so. We are already so paging disable is just to enable the longer mode. We are already in longer mode, so we don't need to do this. Paging is already enabled for us. So I think we just need to do this SSE enabling. And we should do our entry point stuff. We don't need to change code segments because we are already in long mode. We are already in 64 bits. We can keep using the same segment that UEFI puts us in. And I believe we just need to do this, set up our entry point and jump into it. Right. So let's do that. So we want to move into, or move CR4 into RAX. Then we want to so how do we do this? I guess we do something like this, and RX is the destination, and we want them to move RX back into CR4. So move RX CR4. Okay, so that's for SSE enabling. And now we want to set our page map, of course. So how do we go about that? We just move. So here we need page map, and we'll move that to CR3. And then we'll have, I guess that's pretty much it for the page map. And now we just need to set up our entry point and jump to it. So move to, or move entry point, or let me just call it kernel entry, to RX, and I'll basically do jump. Oh, I'm missing something here. Jump RX, and of course I'll need. So here I'm not sure that we can. So NASM or FASM, which is the assembler we used knows that dollar is the current address. So jump dollar means jump to the same address here. I'm not sure if the LVM backend has that. I'll put it in. But I think that since dollar is being used here to determine what immediates are, it's not going to work. So I'll do something like this instead. Catch. And here I can do jump catch. So catch is a label, and I'll jump back to that label. Right, so here I should have page map. It comes from, we should already have that. This should be address space dot root. Cool. And we should also have another one of those here, which is kernel entry. Goes to a register and comes from kernel info dot entry point. That looks pretty good. And as for the registers we are clobbering, I guess we only have RAX. Yeah. That looks okay. Right, so let's build this and see what we get in the output. Well, let's first see what we've... so, unknown use of instruction mnemonic without a size suffix. Jump RAX. Okay. How about now? No. Oh, okay. I remember that there's some shenanigans with this, and you need to put a star there to make it think that it's an actual address. Right. Just don't use AT&T style. Just don't.
Stop it. Get some help.
Right, so here I want to go and find direct 620. Yeah, there we go. So here we have, so we move CR4 to RX, we OR it with 620, we move RX back to CR4, we move RDX that has this value here, which should be our page map, to CR3. Then we move RCX, which has this value here, which should be our kernel entry point, to RX. Then we jump RX, and then we jump to 38A9, which is the exact offset that we are in. So this is our jump dollar, basically. Okay, so now we are good to go for the assembly stuff. So past this point here, we should be in our kernel. So I guess I'm just gonna remove all those lines. We don't need those anymore. So here what we need is actually get key map, or maybe I should call it map key. It's yeah, it's a bit more descriptive to what it is. It's the key of the memory map, and this thing here should return a U size. Yeah, a U size. Map key is U size. Right, and if I go all the way down here and do return map key, Does that work? I think it does. Right. So why is this guy still unhappy with us? Right, so LSB restart. Okay, so now he's happy with us. So here we should do globals.boot services, not servers, services. Exit boot services, and this takes the image handle, which should be under UEFI handle. There we go. And the map key. So we just got that. So let's pass it along. And of course, this exit boot services should return a status, of course. So status equals, it's undeclared, so let's declare that. Here, of course, we switch on status. And we should expect success. And in this case, we do nothing because there's nothing to be done. In case we don't have success, so any other case, we should probably, what should we do? Std log error could not exit boot services, bad map key. That's pretty much the only reason why we can't exit boot services is if we specify a map key that's too old. Basically, the boot services will stop us from exiting if we don't have the latest memory map. And that's what this is for. And we basically return aborted. Let me just spell this out. Status aborted. Cool. And now that we have exited our boot services, we should just execute our assembly here. And with a bit of luck, well, luck, who am I kidding? This will work first try for sure. We should land into this infinite loop here. So that's the expectation at least. Let's build this and give it a run. Okay. Yeah, it's going to work first try, of course. So no restart. No restart. Shit. No restart. I guess there's no. Wait. No. Reboot? Okay. And cool. And I want to have CPU reset. Okay, so we do have a triple fault. We are doing something that we should not be doing. Okay, so all this time I've actually avoided doing this, but I think we are going to need to use a debugger. Be right back. Right, so I went ahead and cloned EDK2 and built it in debug so that we can get ovmf.fd, which is what we use as our UEFI firmware. It took about 5 minutes, but I've been too lazy to do it all this time we've been working on UEFI stuff. But seeing that we need we now need the debug information. Well, it's not that bad at timing. So let's go back here. Should also probably put this into debug mode. So I think that's the optimize, and it takes debug as a parameter. Right, so let's move to here. Okay, and let's do something like this. Let's do lvm objdump -d intel and build boot.uefi. And if we do, so we should look for 620. Cool. So our code starts here at offset 199F. So if we know where the UEFI bootloader or UEFI firmware loads our bootloader, we could add this offset to it and put a breakpoint there, so we can follow along what's happening under the hood and why we are getting the triple fault. Right, so to do that, we want to go over here. I've changed the command here to point to our ovmf.fd that we've built as our firmware. And I've added this debug-con file debug.log to basically have this go to a file so that we can tail it. And let's do just that. So tail debug.log. Cool. So now if I run this, I should see something, which I don't. So by the way, all the steps I've done are basically taken from this article here, debugging OVMF with GDB, and slightly adapted to my needs. So here, the thing I'm missing, I think, is this here. So let me just take that and probably just add that there. Yeah, needs a space. And we should see, yeah, so we are seeing something on our debug tail. So it's slower than usual, which is normal. And okay, so we do triple fault again. Right, so now what I'm gonna do is I'm gonna make QEMU wait for a GDB server. Then we're gonna create that. So here I'm just gonna clear this GDB target remote already 4. Cool. So now we are in, and if I just do continue, we should see that it's executing. So we haven't put any breakpoints yet, but for now that's fine. Right. So we do have our log file, and what we are looking for here is this line here, loading driver at the driver address and the entry point of that driver. And of course it says that it loaded boot.uefi, which is our file. So that's pretty good. So what we want here is take this entry point and just put a breakpoint. The thing is, it basically, since we are using a virtual machine, it's gonna try to reload things pretty much the same way, and we'll have our boot.uefi at pretty much the same address every time. So it's going to move fairly, it's going to move a bit in memory, but it should be always around the same address. So let's continue and see if we hit that breakpoint. It's taking its time, so let me just check on it. Okay, okay, so we should have our breakpoint there. Cool. Yep, that looks like our code. So we now go back to, or we create a new thing here and go LVM opstamp. Can I just get that? There we go. And if we look for, oops, it's not what we wanted. If we look for 0620, there we go. So we want our breakpoint to be at 99F. 99F. So I guess we could do something like this and 99F. Right, so continue. And we get our breakpoint at 99F. So if we try to execute the next instruction, so for some reason, okay, so now it works. It's okay. It's not, okay, so it's not scrolling correctly, but it works. So now we have loaded CR4 into RCX or RAX. So hold on. Okay, so all of our windows are a bit off, but that's fine. So if we go next instruction here, we should do the OR. Okay. And we have put it back into RC4. Just to make sure of that, I'm going to do info registers. And that should, in theory, give us CR4. Yeah, and I think that's the value that we needed from it. Cool. So now we are going to move RCX to CR3. So what value does RCX hold? It's this one, 61B4 and 3 zeros. And if we go and do something like print as a long pointer, 0x61B 4 triple zeros. Yeah, that's not what we wanted to do. Actually, we want this to be printed in hex, and we want this to we want 512. Yeah, after that. Oh, yeah, of course. So that should be something like this. Cool. Yep. So here we have, this is our root or our kernel page map root, and we have one first entry here at 61 AE 3 zeros, and we have a second entry at the very last entry, so index 511, 61B 3 zeros. So that should be okay. So now if we take a look at those entries, so let's take the last one, maybe. So B3 3 zeros. Okay, so now we have 61B2. Let's take a look at that. And here we have 61B0 and some others. So let's take a look at the one at 61B0. And here we have a bunch of pages that are mapped here. So let's choose one of those and take a look at it. So let's go 800 BE triple zeros. Okay, so we do have a bunch of zeros, which is weird. I have expected there to be at least a page being mapped. But okay. Let's take a look at one of the other ones. So 0 and 1. This one, yeah. 3 zeros, 1 and 3 zeros. Cool. Okay, so we do have something there. Right. But now if we go into that and set our page map, okay. So here we could not read memory at whatever that address is. And if we do something like print, or let's do print instruction at RIP display. Is it display? Okay, so we cannot access memory at address RIP. So our execution or instruction pointer is pointing to memory that we cannot access, and we can make sure of that if I open a calculator and we go here and do 6177 3 zeros, for example. You can see that we are at 100-ish megs of memory, and that's pretty normal that we cannot access that, since if we go back down here, we've only mapped about 64 megs. So anything above 64 megs will not be mapped in our current setup. So let's change that to, let's be generous. Let's do 512. Let's do 512. Okay. So let's go to GDB. Let's exit from that. Let's go back here. Let's rebuild. And let's run this again. So I'll run it a first time just to get the address where it's loading us. So I'll just hit target mode before, continue. So just want to run it through once to get the address where we are getting loaded, and then we are going to set our breakpoints. In the meantime, I'm just gonna go here, clear and redump our file. Look for 0x620 and check that we are still at the same offset, so 99F. Right, so if we go here, GDB, what's going on? What is going on? So we are executing some weird instructions. Is that it? I think we are executing some weird instructions. We haven't stopped though. We haven't gotten the triple fault though, so that means that that was due to us not having mapped enough memory. So now if we go back here, try to find where this is loaded. So it should be there. And I'll just go back here and probably rerun this first. go back there, target remote 134. Yeah, of course, go again. So hardware breakpoint, put that in there. And we should just put 99F as our second breakpoint. So let's continue. Right, so it's still executing. And we still haven't hit our breakpoint for some reason. Why is that? Where did it load us? Okay, so it moved us in memory a bit, moved us one page over. Right, let's try again then. So target remote 134, and this time here I'm gonna do 7099F and continue there. Okay. We should stop right now. There we go. So here we are. Should probably do this for it to refresh. And we should have, so if I just continue here, we should hit our other breakpoint. Cool. So I'm gonna hit with next instruction a few times, just so that we can move things along. And here we should be, yeah, so here we are going to move RCX to CR3. Okay, cool. So now we are going to move RDX to RAX, RDX being this value here. So it is the entry point of our entry point of our kernel. So if we hit with a next instruction again, now it's going to jump RAX. The only problem is that I am expecting here to see the code of our kernel, but that's not what I see. We might have a problem. Yeah, we might have a problem. So let's go here, frame buffer, don't care about that. Kernel. So kernel segment, we get that. We get the virtual address and the physical address from that. We print that we are going to map the segment, and here we go ahead and do num pages. What? What is going on here? And we should not do this now. We should do this after we finish the loop. Hold on, I'm just gonna put this as info just so that we can follow along in the output logs. Here we should map our kernel segment, and yeah, so that should look, or at least that looks okay. That should be fine. Let's try this again. Right. So I'm I guess I'm gonna have to target remote 134 again and just continue. Okay, almost there. We have a breakpoint. We continue from that breakpoint. Right, so we have our kernel segment at 61B4000, and we map that to our actual entry point. Wait, what? Hold on. Hold on. Yeah, I'm going to need a breakpoint for that. Where were we loaded? We were loaded at here. So let's try that again. So info breakpoints. So del 1, 2, 3, and 4. Should have none, and I should probably do first a target remote 134 and hardware breakpoint there, and I'll add another one there just in case we get moved in memory. Let's see where if we catch the breakpoint. Okay. Okay, so we did catch the breakpoint, and just gonna do 99F. Yeah, I'm not sure that we are still there, but so 0620 99F. Cool. So let's continue. Okay, we do have our breakpoint there. We're gonna advance our instruction pointer a bit. Okay, so now we are going to move RCX to CR3, RCX being 61B4000, and we expect our kernel to be at 61B5000. So if we just go ahead and do print, let's just dump it as hex instruction 0x 61B5000, and there we go. We should have push. Let's get 5 instructions from that. So push RBP, move RSP, whatever, and then we jump back to that same address. So this is the actual code that we have in our kernel. So the physical address points to the correct code. So now let's advance our pointer. And now if we do the same but with the virtual address, which is 134 FC 00 and 2 and 4 zeros, we should pretty much see the same code as before, except we don't. So what is going on here? Maybe the address is not correctly mapped. That's a possibility. So let's follow our memory map. So X, or rather print as hex of a pointer of long, and our memory map is at B4 3 zeros, which is what we've put into CR3, and we want to get that 512 elements of that. Cool. So we know that our kernel address has, so the upper bits are all ones, so we should be at the last entry here. So we'll follow that. That's 3. And all of the entries are 0 except the last one, so that should be the one we want. Okay. And here, if I open calculator here, so let me just 4 FC 2 zeros and 2000. So if I go here, we take 9 bits, that's the last entry. We take another 9 bits, that's the last entry again. And we take 6, 7, 8, 9 bits again. So that's the last entry. Wait, no, hold on. I'm delusional. So we should ignore all the top bits. So let me just do this. There we go. So we should take 9 bits. That's the last entry, and then 9 other bits. That's again the last entry, and then we have 9 bits, so 4 and 5. And that should be, so what is that? Let me open another calculator here. Go binary and do, so 1, 1, 1, 1, and 5 zeros. So that's 480. So that's the 480th entry. And since we have all zeros before that, I guess it's this one here. So let's take that. So it's B0000, 4 zeros. Okay. And after that, we take 9, so 3, 3, and 3. 9 other bits for our page table entry, and that's 10, so that's 2. We index from 0, so that should be 0, 1, 2. And it should be this one here. So 8,000, 2,000. Right. So if we do 8, 1, 2, 3, 2, 1, 2, 3. Aha. No, wait, hold on. This should be the address of our... Yeah, we should not try to... This is not a table. This is not a mapping table. This should be our actual address. But this is not the address of our kernel. Our kernel is at... we've seen that in the logs somewhere. Yeah, so our kernel is loaded at 61B5. Huh. So something else is overwriting our kernel mapping to this address here. Huh. Okay. Very interesting. Very, very interesting. So let me go back. So that means that we have under write entry, somewhere here we should check if the entry exists or not before writing to it. Right, so if entry.present, we should log.warn overwriting a present entry. So what should we do here? we should probably do old p address would be, so 0x and this in hex, and with 0x and this in hex again. And this should be entry.getAddress. That's pretty cool. And the actual physical address that we want to write. Yeah. I probably have to do something like as U64 bitcast of physical address, just to avoid any whining from the compiler. And with this, we should probably see when we try to overwrite a page on our memory map. So I'll just run this without the debugger for now. Actually, hold on. I'm just going to do something here. I'm just going to remove this thing here, just to speed up things a little bit. Okay, let's see. Aha! Would you look at that? So we are overwriting the entry, which is our kernel, with some other entry here. Huh. Okay, cool. So now can we know where that entry comes from? Do we have any way of knowing? I guess we could just track all the calls to mmap and put something above them. But we know for sure that it should be somewhere below this. So it can either be our frame buffer or our identity map. So let me just do log.info mapping FB. Yeah, that should do the trick, I think. And here I'm gonna go down and do something like mapping identity. Yeah, let's call it that. Right, so let's run it again without the debugger, just see what we get. And I'm pretty sure, well, chances are it's the frame buffer because our entity mapping, yeah. Would you look at that? So mapping frame buffer overwriting a present entry with whatever that is. I guess that's part of our frame buffer buffer. And then we map the identity entries without any warnings. So now the question that I have is, why do we do that? How does the frame buffer decide its virtual address? So where does the FB address come from? FB address, and that comes from kernel info FB address. Okay, and that should be set to something here. Right, so all this comes back down to what we've put in our linker script. And okay, so we put our frame buffer 2 pages above where our entry point is. Would you look at that? So here we have FC002000, and here we have FC00000. That's bad. That's bad for a number of reasons. So let's give it a bit more breathing space. Let's put it somewhere. We know it's not going to do any harm. And actually, let's move the boot info to FC. Oops. FC 00. There we go. And let's actually also do env. Well, env, not end. And that should be just 1 page over. So we can have boot info, env, and our entry point directly. Right, so with this, we should probably just rebuild and recheck what we have. Right, so now we expect there to be no overwrite warning from our memory map stack. Okay, fingers crossed. No warning. No triple faults. This might mean that we are good to go. We never know. So let me just go back here, ask it to wait for the debugger, and go back here. I'm just gonna reset my GDB thing here, and hardware breakpoint. Did I forget to copy this? Seems like it. All right. So that, just gonna put a breakpoint a bit further, and then we'll run that. Just gonna make sure in the meantime that we have our offset is still the same, basically. So 0x620. And our offset is still the same, indeed. So I guess we should go here and do FF9. Is it 99F? Shit. 99F. Cool. Run that. Okay, so drum roll. When we reach the move RDX into RIX, we should expect GDB to basically show us our kernel code. And indeed, it does. Would you look at that? So here we are going to jump RX. We are going to go to that virtual address there. And at that virtual address, we do have the code for our kernel placeholder. So if I hit C here, it's continuing. If I hit Control C to stop it, we can see that it's still jumping to that same address there. We are officially in our infinite while loop. Our kernel is officially running. Well, at least our kernel's placeholder. But yeah, it's very, very good news. That means we have pretty much achieved what we needed to achieve. We have, I guess, functionality parity between our BIOS bootloader and our UEFI bootloader now. Cool. Very cool. Very, very nice. I can officially check this off. And now we have functionality parity between our BIOS bootloader and our UEFI bootloader. I'm very happy we got here with minimum changes. Most of the code we wrote worked seamlessly, like a charm. Our virtual memory mapping was working great. We just had some problem with the frame buffer. Well, on this high note, I'm going to leave to think about the kernel, how to get there, formulate a coherent roadmap to get there, just to have videos that are nicely structured. And as always, if you've liked this, hit like, leave a comment, subscribe, all the good stuff. That's what keeps the channel going. I don't do this for the views or for the money or for anything else. Actually, there's no money coming from this. And I could have done this in a lighter format where I just show a code that's already done and working with having to explain all the steps and go into technical details, which would have taken me a lot less time, but I chose not to do it, just to give you guys the full experience of what it is like to work on subjects like this. So yeah, the engagement or the comments and likes are what keeps the project going. So thank you guys for that. And if there are any topics you want to see me cover, or you have ideas about things to do for the kernel, well, let me know them and I'll take all of them into consideration. Until then, and in the meantime, take care of yourself, have fun, keep on building. Bye now.